Hello, this is Around the World in 80 Telescope, the live webcast in the 100 Hours of Astronomy. So, we are still at the European Southern Observatory. The night is getting longer, but we are now going to Japan. So, next one that we are going to start now is the Hinode space mission. We are going to the base, to the control center. But first we will start with their video.
Our lives depend on the sun. Shining modestly on nearly every form of life, day after day, it's so close to us that we're prone to overlook the sun's importance. Despite its modest appearance, however, the sun is alive and roiling with activity, unnoticed by us. Many of the sun's phenomena remain a mystery, awaiting scientific explanation. Both ground-based telescopes and observation satellites have been used for studying solar activity phenomena. Japan has successfully carried out 2 solar observation satellite missions, significant achievements including revealing the mechanism behind solar flares. However, one important mystery remains unsolved. Why does the corona reach temperatures of several million degrees Kelvin? Finding the answer to this question will not only deepen our understanding of other stars, but it will also represent a major discovery that provides us with a key to understanding the mechanism of the entire universe. In this age of accelerating space development, the ability to predict solar activity is becoming increasingly more important because this knowledge helps to protect satellite equipment and astronauts engaged in extravehicular activities against the dangers of solar radiation. The Japan Aerospace Exploration Agency and the National Astronomical Observatory of Japan, in collaboration with space agencies in the US and UK, launched a Mu-5 rocket bearing a solar observation satellite on September 23, 2006. The satellite, named Hinode, conducts continuous solar observation from a sun-synchronous orbit, hovering above the border between day and night. Hinode carries 3 telescopes. The first is a Solar Optical Telescope, or SOT. It boasts the largest aperture of any orbiting solar telescope. Making up the main body of the satellite, SOT is a reflecting telescope 50 centimeters in diameter that can produce very fine images of the sun. It can also measure magnetic fields on the solar surface. The cylindrical object next to SOT is the X-ray telescope, or XRT, and it's used to observe the sun's corona. The XRT is not only capable of detailed observation of the coronal structure, but it is also sensitive to the corona's wide temperature range, which runs from 1 million to 10 million degrees Kelvin. Finally, Hinode also has the Extreme Ultraviolet Imaging Spectrometer, or EIS, and it's placed on the other side of the satellite from the XRT. EIS is an instrument for observing the sun's ultraviolet rays, separating them into a spectrum like a rainbow. EIS identifies the chemical elements present above the sun, as well as their speeds, temperatures, and densities. Hinode observes various solar phenomena using this trio of telescopes. Here are amazingly fine images of the sun's dynamic activity, as observed by Hinode. Let's take a look. This is a full view of the sun's photosphere, captured by another spacecraft, SOHO. What will it look like when viewed by Hinode? Below and to the right, the Earth can be seen at the same scale. Hinode's Solar Optical Telescope captured the photosphere in great detail, providing us with a totally new perspective of our Sun. This is the Sun's chromosphere as observed in a calcium H-line. On December 13, 2006, Hinode captured a massive solar flare. It also captured an X-ray view of the flare. Shown in the right half is the chromospheric view, while the left half offers an X-ray view of the corona. Plasma heated by the flare is clearly visible. Hinode has revealed that areas of the Sun formerly considered inactive are in fact very active, with an endless series of small explosions. Hinode, the rising Sun, is revealing a succession of unexpected perspectives of the Sun.
We are now going live to our friends in Hinode in Japan. Moshi moshi.
Moshi moshi.
So, could you please tell us who you are?
Hi, I'm Takashi Seki, associate professor at the National Astronomical Observatory of Japan, and here's my colleague.
Hello, I'm Alphonse Sterling, and I'm a scientist at the Marshall Space Flight Center, actually in Huntsville, Alabama. But for the Hinode project, I'm stationed here in Japan for a large part of the mission, already 2 years.
So we've seen in the video, we've seen in the video you have quite a whole observatory up there, going from the UV, X visible. So what do you do? What do you do in terms of solar physics?
Well, with visible light, we can study the so-called photosphere, which is the visible surface of the Sun. If you look at the Sun with your eyes, you'll see the surface, and that's so-called photosphere. And that's where many things like a sunspot and so on are going on. And that's what we observe with a visible telescope. And with UV and then with X-ray, we can see the upper layers of the solar atmosphere, where many more other things are taking place, some of which are a key process to explosive event called flares and so on. And actually the corona itself is a very thin layer of the solar atmosphere, which is very hot. We think its temperature is in millions of kelvins. And why it's so hot? It is one of the biggest questions in the solar physics. And that's one of the scientific targets we are addressing. Can you think of anything else, Alphonse?
Yes, that's exactly right. One thing that's very key, or a key puzzle in solar astronomy, is, as Dr. Seki was saying, how you heat the outer atmosphere of the Sun, how you heat the corona. And we've known for a long time that this energy comes from, well, the center of the Sun, and it gets transferred up through the surface of the Sun and into this outer atmosphere that you can see here, and heats it. But we haven't been able to detail the exact processes about how this goes on. We know that it deals with the magnetic field of the Sun, the same thing that causes sunspots like this. And for the first time with Hinode, we are able to look continuously with the same observatory without the atmosphere bothering us at the processes at the lowest levels of the Sun, so the photosphere and chromosphere, which you see here, and also the magnetic field and how it's reacting to the motions in the lower atmosphere. And then we can follow that from that low level, which we see in white light and lines like that, in through the ultraviolet regions, which is sort of a medium level between the lowest level and the hot outer corona, and then out into the corona. So with Hinode, we can follow the action